So we've seen these standard integrals before, but now we're going to look at what happens when there's a multiple inside one of these functions. And it's quite easy to figure it out. For example, if we thought of derivatives, I'm going to start with derivatives first. I'm going to pick sine of 3x. If you did this derivative, do you see that you would have a simple chain rule? Your outside function is sine, and your inside function is 3x. And with that simple chain rule, you'd say, well, the derivative of sine is cos. Keep the inside the same, and then you would multiply by the derivative of the inside, so you'd multiply by 3. And if the inside is a linear function, a line, then its derivative is always just a number. That means we could work backwards easily. Because if you were working backwards, what would you have to do to undo the multiply by 3? Divide by 3. So we'll see here, like, e to the kx. Normally, if you did the derivative, you'd have to multiply by k. So doing the integral, we have to divide by k. Cos of kx. If I was doing if I was doing a derivative, I'd multiply by k. But since I'm doing an integral, I divide by k. So anytime you have an inside function that's a line, you can integrate by just adding a division for that chain rule. That chain rule would normally have a multiplication by a number. So integrating, you can undo that by dividing by the number. Right? And we talked about this the other day, where you think of x to the minus 1 as a power rule and run into this crazy divide by 0. So you have to remember that it is the natural log. And this is the other note that I was showing you, that you are just compensating for that chain rule. First one, we have a 1 over x. There just happens to be a 12 in front. Question?
Can you go a little bit up?
Yes.
But why in example 2 there's not the, how it's called?
Okay.
No, I mean the...
There should be.
Okay.
Yeah, it's just missing. Thank you for noticing.
I don't know.
Mm-hmm. In that one, there could be. So but technically, it doesn't occur as much in this case, because if I wrote it like this, integral of 1 over kx, okay, dx, that's just a constant in this example. It's not really inside. So I could just pull it out and do it like normal anyways. And then I would get natural log of absolute value of x over k the same way. And then the question is, well, why isn't there like a k inside? We could examine that a little bit as well, but we don't have to we don't have to worry about it in that situation. Let's see. Okay. So when you have a 1 over x and it's hidden with a number in front, well, that number is just a constant. You could pull that 12 out in front and then get 12 natural log of the absolute value of x. So here, you could bring that 1/2 out in front. Now here, e to the 5x, if you were doing the derivative, you would have a simple chain rule where you have to multiply by 5. So doing the integral, you're going to have the simple chain rule where you have to divide by 5 to compensate for that. And we could simplify that to 1/10 if we wanted to. Now you can only easily compensate for the chain rule when it's a line. When it's a function, it gets a little bit messed up, but we'll get there. So for each one of these ones, you can integrate them all separately. Add 1 to the exponent and divide. You see the 1 over x, so that's going to give us the natural log of the absolute value of x. And we still have the 3 out in front. And here, e to the x over 3, if you had it as a derivative, you would have a chain rule where you multiply by 1/3. So here we have to compensate for the chain rule by dividing by 1/3. And then I forgot the plus c here, so when I simplify it in the end, I'll write the plus c. Okay, I'd like you to try the next two. I'll put up the answers in a bit.
Sorry for the interruption, but Mr. Peggy, come to the office, please.
I'll put up the next one. You can, if you haven't finished it, don't look yet. Check how you did on the last one. So we can compensate for the chain rule because the function inside is a linear function. Y equals mx plus b. And anytime you have a linear function, when you do the derivative is just the slope. It's just the number. So because it doesn't have any x's involved in it, we're allowed to compensate. If it was a parabola, we get to a whole nother level of integration that's coming later. So we compensated, these first examples that we did, we compensated when there was like a line that was just mx, no plus b. But can you see that if you had mx plus b, or ax plus b, it'd be exactly the same. So we're just going to look at some derivative practice, right? How are you feeling? Are you feeling like you want to do derivatives on your own, or do you want me to just put the answers up and quickly copy them down? You want to do them on your own? So each of these has an inside function that's a line. Find the derivative of all of them. So in all of these, you would have a chain rule, right? But the chain rule would be really easy. You just have to multiply by whatever the a value is. So if you had to integrate this form, do you see that you could do it with just compensating by dividing by that a value? I really highlight it here, I take out a highlighter, I had an a value there. With the derivative, I would have to multiply by a. Here I have an a value inside the function. And the derivative of all of this inside is just the a. Right? Derivative of all of this is inside, but its derivative is just the a. Every single time that you have a line inside. If you did the chain rule, because of this a, even though there's all of this other stuff is inside, the derivative of that will just be a. So we can take this and say if we get something that looks like this with an integral, we just have to undo the chain rule, which would mean we'd have to divide by a. Everybody good here? So here's our power rule. It's saying that if this is your inside function, right, this is inside, its derivative would just be the a. So now we compensate by dividing by a. Everything else is the same, right? So what was our rule for power rules? Add 1 to the exponent and divide by the exponent. But now we also have to divide by the a. So for this first example, I would start by writing that cube root as a 1/3. It's a power rule. It's a power rule that would, if I was doing the derivative, would have a simple chain rule that I'd have to times by 5. So now, undo things. Undo the power rule by adding 1 to the exponent and dividing. And then I also have to divide by 5 to compensate for that chain rule. So here's our second example. Again, I would take the time to write that power of 8 on the top as a -8. If I was doing the derivative, I would have a chain rule where I'd have to multiply by 9. But now I'm integrating. So power rule integrating, add 1 to the exponent and divide, and then also divide by 9 to compensate for the chain rule. Add the plus c at the end, and you're fine. So you could compensate for this chain rule in any function that you know the derivative. Trying to think off your purple sheet, which would be the not nicest one to do this in? One of your inverse functions? I'll do one for fun that's really not nice. Happy. See if you can pick it out. Not to take out your purple sheets. See if you can figure it out. But we'll do these last two with sine and cos first. Wait a minute. No, we don't. Well, we have sine, cos, and e to the x. We've got 4 examples to go. So we recognize this as 1 over x but instead of x, you have 3x minus 5. So we can pull that 15 out. 1 over x is the natural log, so this one is going to be 15 natural log, and I'll add my absolute value bars there. But then, because I have a chain rule, I need to divide by 3 as well. Same thing with e to the x. If you pull the 7 out, still need the dx here. And the derivative of e to the x stays the same, but there would have been a chain rule, so I have to compensate for that and also divide by -3. So I find for me, what's helpful with integrals is if I have an idea that I can do the derivative of, I think about what would I do if I did the derivative, and then I say, okay, I've got to undo that now. So then I just work backwards and compensate for everything that would happen as a derivative. The other nice thing about an integral is once you've done the integral, you can always do the derivative to double check if you get what you started with. And I'll put up these answers of sine and cos there. Exactly more of the same. So here's the one with integral sine. You'd have to divide by 6. To compensate. I'm trying to. Do you want a challenging one where I try to be as sneaky as possible and give you one and see if you can figure it out? Okay. Well, I'll give you the answer for the last one. Did I not hit the button? Here's the last one. There we go. Here's our last one. No problem. Here's our challenge. Integral of 32 over 4. I just want to get more and more creative. Should I like not go too overboard? Just overboard a little?
Okay. Go fully overboard on that second one.
No, we'll just do one. Not crazy. So. Dx. So you're going to need your purple sheet.
When were the purple sheets handed out?
They're just in your notes, but they were handed out.
There's
Yes.
There's some right there.
Yeah. So see on your purple sheet if you recognize this derivative. Somewhat obscured. It's going to be on here somewhere. It's got a square root.
It's one of the inverses, right?
So, yeah. It's one of the inverses. So the derivative of secant inverse of x is 1 over x squared minus 1. And, but is that x squared minus 1? It's factored as a difference of squares. So that's why I was getting creative. It would have been even harder to see if I would have simplified this as 5x plus 4 and 5x plus 2. You see where integration gets really hard really quickly? If someone's like, oh, I simplified a little. You're like, no. It makes it so much harder. So yes, the answer to this one would be 32 could be pulled out. So the 32 in front, secant inverse of 5x plus 3, but then you'd have to compensate by dividing by 5. Let's see. I don't think they would ever. They tend to avoid a lot of the inverse ones because they're tricky. So you don't see them very much on your exam. It's not like, oh, this exam we're just going to focus every question on an inverse derivative. Because we know you've practiced them so much over the years. All right, a few more notes, then we're going to do a little something different with a video example. Sigma notation. As we're getting ready for the next idea of this unit. Idea 1 of this unit is just, could you work backwards? Perfect. Next, we're going to talk about areas under curves, and then why it all comes together. Do you remember sigma notation? No. Okay, this big sigma sign is a symbol for, hey, find a sum, add things up. And in the sum, it has a starting point on the bottom. So start when k is 1, end when k is 4. And here's your formula. So when k is 1, it would just be 1 squared plus 3. That's the first term. Then k is 2 squared plus 3. So you plug 2 into the formula. Then you plug 3 into the formula. Then you plug 4 into the formula. And if we put that all together, it's equal to 42. Now we're going to be adding up a bunch of things, so we're going to be using this sigma notation quite a bit. If you have this as a sum, how many things are we adding up? 6 things. Does it make sense then to start when k is 1 and go till k is 6? What formula would you have to have here so when you plug in 1 you got 1? When you plugged in 2 you got 2? What formula would be in there? It would just be a k. Now, this is the most predictable answer. I could make one that was less predictable. Let's say my formula was k minus 5. What would k have to be to get a 1 to start with? So then I'll start at 6. And then what would I have to have at the top to end with a 6? 11. Okay? So this would be another answer that's completely correct, just not as intuitive, but still right. Okay? I want to point out one thing. When it's written this way, k equals 1 to 6, people have no problem saying there's 6 terms. When it's written this way, it's not as easy to see. And what do you think the number one mistake is when they say, how many terms are there? People say, oh, 11 minus 6, there's 5. Can you see yourself doing that? But 6, when you do 11 minus 6, you don't include the 6. The 6 is taken away, right? There's only 5 numbers that aren't included. 1, 2, 3, 4, and 5. 6 is included. So when you do this, you have to say, well, it's not 11 minus 6. It's really 11 minus 5 because the 6 was included to give you 6 terms. And then there are some fun formulas. Do you remember adding these up with arithmetic sequences in grade 11? Where you add, if you wrote this backwards, you have 7 6 times. So you can just add the first one, which is 1, the last one, which is n, times by n times, but that would count it up twice, so you divide it by 2. That is just a little note. You want to look it up. That's related to an arithmetic series formula from grade 11. Right, here is a simple proof. If you added all the numbers up to n, that would be the sum. If you added all the numbers up to n backwards, it would still be the sum. But if I added these all up, each one, n plus 1, and put them in like brackets, this one would be n plus 1, and these ones, if I add up all these columns, I get a whole bunch of n plus 1s. And the sum plus the sum will be 2 sums. Does it make sense that all of those n plus 1s, there are n of them? Because you had n terms to begin with, you now have n plus 1s. And then to get the sum, that would be 2 sums. You divide it by 2, and you would get just 1 sum. And underneath that formula are 2 other crazy formulas. Crazy formula number 1. Okay. This is like adding 1 squared plus 2 squared plus 3 squared, dot, dot, until we got to n squared for any number. You could add up to 10 squared, you could add up to 20 squared, you could add up to 30 squared. It will always equal, right, if I wanted to add up to 10 squared, it'll be 10 times 11 times 21 divided by 6. That's a crazy formula, right? If that intrigues you, look up some proofs. Why does that work? How does one find that? And then even crazier, look at this one. You did 1 cubed plus 2 cubed plus 3 cubed plus dot, 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 all the way up to n cubed. It's exactly the same as adding up to n, but you just square it. That's weird. Okay, check it out. Let's just do up to 4. If I added 1 plus 2, if I just added the first 2, do you see that you would get 3? If I add up the first 2 cubes, you get 3 squared, which is 9. If you add up 1 plus 2 plus 3, you get 6. If you add 9 plus 27, you get 36, which is 6 squared. We do 4 of them. You add 1 plus 2 plus 3 plus 4, you get 10. 4 cubed is 64. 64 plus 36 is 100. It's just kind of, I don't know, this is where I love math, is when you get these patterns that happen that are like, wow, why is that related? How does that work? How does one come up with proving this? And then we have some properties of sums. If you're adding inside of a sum, you could just sum them separately. Same thing with a constant. If you're multiplying everything, if you think about, if I was adding 5 numbers, or 4 numbers, and they all had a 5 in front, does it make sense that you could factor out that 5 and just have it in front in the beginning?